Hello everyone and welcome on today's video. My name is Wouter Pere, I'm the founder and main developer of GHEtool Cloud. And today we will be continuing our discussion of the feature calculating the required borehole depth, and more specifically an error that can occur rather often, which is the gradient error, the unsolvable due to the gradient error. And this video will consist of two parts. We will first have a short recap of what this method is. Then we will go into detail about the importance of the temperature gradient and why this can sometimes lead to an unsolvable problem. And then in the second part, we hop into GHEtool Cloud. We run a couple of simulations and we'll see how we can cope with this error in practice. So stay tuned for the second part as well, but let's start with the very beginning. So if you have not watched our previous video, you can do so, it's linked in the description below. But conceptually, the method to calculate the required borehole depth is we start with a bore field with an initial depth. We calculate the temperature profile. We check if the temperatures are within the temperature limits we have set. If this is not the case, we drill a little bit deeper. We recalculate the temperature profile, and this process we keep iterating until we converge to a solution in which the temperatures of the fluid stay between the minimum and the maximum threshold we have set. Now, this is how it's done conceptually. Now, there can occur an error. And to explain this, let's assume that there is a constant ground temperature. So in that case, we calculate the temperature profile and we see that our maximum average fluid temperature is above our threshold. So in case of passive cooling, typically above the 17 degrees Celsius threshold. So what our method does is it will increase the borehole depth. So we will drill deeper, and by doing so we will increase the total borehole length. And if we do so, we also decrease the power exchange per meter. And we have the same power demand for a bore field, but we now have more borehole length. So we extract or inject less power per meter from the borehole. And this leads to a lower maximum average fluid temperature. Now, if you're not that familiar with the relation between the power and the fluid temperatures, please watch our video on the short-term effects, bore field physics. It's also linked in the description below. So this is the case for a constant ground temperature, and we will always converge to a solution there. But if there is a temperature gradient, we again have the same physics. So our temperature is above the threshold, we increase the borehole depth. By doing so, we increase the borehole length. This leads to less power per meter, and hence we have a lower fluid temperature. But there is a second aspect that comes into view, namely that since we are drilling deeper, and since we assume that there is a temperature gradient, so the ground heats up when we go deeper, drilling deeper causes us to have a higher average ground temperature. So this will increase the maximum average fluid temperature. So what we can see is that if we're limited by the maximum average fluid temperature, what we actually want is to have more boreholes instead of deeper ones. Because if we drill deeper, the ground will be warmer and it will be harder to cool or to inject heat into the ground. So to illustrate this, here we have a temperature profile for the constant ground temperature. So what you can see here is we have indeed a constant ground temperature of almost or a little bit over 10 degrees Celsius. And then we have our maximum average fluid temperature. And as you can see, if we increase the borehole depth, so we drill deeper, and this is of course a very extreme scenario, but you understand the point that if we are very shallow, we have a high power per meter for a bore field, so also very high peak temperatures in cooling. But if we increase the borehole depth, this temperature drops off rather quickly due to the fact that we have a lower peak injection power per meter. So this is the case, and you can see that it converges to a constant distance, which, if you recall, is equal to the, or due to the borehole thermal resistance. So it converges to a constant. Now this is for a constant ground temperature. Now, in case you have a temperature gradient, you can see that your ground temperature, it increases in depth, and we have our same fluid effect. So when we increase the borehole depth, our fluid temperature decreases. But of course, we need to combine both effects. So our fluid temperature decreases due to the fact that we now have more borehole length, but we need to add the ground temperature, so we have here a combined effect. What you can see is that indeed the peak average fluid temperature, it decreases, and the fluid itself keeps decreasing, but due to the ground temperature, we are again increasing in the end. And this it is the distance between this green line here and the blue line, which is actually the borehole thermal resistance again. But it's not a parabolic shape, but you can see that it decreases and then increases again. And this is due to, or this is crucial why there is actually an error or problem there. Because imagine, and this is of course schematic, but you have two boreholes in this case, and this is the curve from before. If your temperature threshold is actually lower than this minimum, this means that no matter the borehole depth, you will always be warmer than the maximum allowed temperature. So in this case, you will get an error, well, the problem is unsolvable. And what you then need to do, because there is no depth below the threshold, is you need to increase the number of boreholes. So instead of going from 2 we go to 3. This lowers the curve, because now imagine that you have 50 meters of borehole depth. In this case, this led to 100 meters in borehole length. In this case, it's 150. So the effect we saw earlier of the fluid is way more pronounced, because we now have 3 boreholes instead of 2. So our depth is multiplied by 3 instead of 2 to have the total borehole length. And this causes the whole curve to drop, and we're indeed lower than the temperature threshold, so we can solve this problem. Now perhaps you can notice that we can cross it at 2 times. So if we increase the depth, at one point we reach the temperature limit, so your bore field is sized correctly. If we then further increase the borehole depth, we are below the temperature threshold, so you can say that your bore field is oversized. It's too big. But then if you go even deeper, your temperature again increases due to the ground temperature, and we again end up with a bore field which is correctly sized. So both points actually are bore fields which are correct. They are both at the temperature threshold, but of course you typically want this solution, since it's cheaper, it requires less drilling, etc. Now the numerical optimization on why GHEtool gives you this point is a little bit theoretical. We will not go into that in the video, but if you're interested, it's written in short in the article. So now let's jump into GHEtool Cloud, design a couple of bore fields, and see how you can cope with this gradient in practice. So here we are in GHEtool Cloud. I created a new project with, although the parameters are not that important, I'll briefly show you. We have 2 watts per meter Kelvin for the thermal conductivity. We have 5 boreholes of 100 meters deep. A borehole thermal resistance is 0.15. And we have a thermal demand of 15 kilowatts in heating and 10 kilowatts in cooling. So now, if you want to use the method to calculate the required depth, you select it here. And you can see that there is a warning popping up stating that you need to check the ground parameters. Now, we discussed this earlier talking about the ground parameters, but if you're using this method in a very heterogeneous ground where there are clay layers or bed conducting layers, it can be useful to enter them as different ground layers, because then the algorithm will at every iteration recalculate the average ground thermal conductivity in order to find you the best solution. If you're just using the assumption of the homogeneous ground, it's best to, once the method is done, you check manually whether or not your thermal conductivity still is correct for the newly calculated depth. But in this case, we will assume it is to save some time. And let's calculate it now. So this is the result we then end up with. You can see that we need to drill 116 meters deep, which will give us 115 meters of borehole length. And as you can see, we're indeed limited by the maximum average fluid temperature in this case. Now imagine we say, well, we don't want to use 5 boreholes, we want to use 4. So we're going to check, can we do this cheaper? Can we remove one borehole? And then we end up with a calculation error indeed. We say, well, no solution can be found due to the temperature gradient. And why is that? It's because if we go back, we are now at the maximum temperature. If we decrease the number of boreholes, the algorithm will try to drill deeper, which will increase our average undisturbed ground temperature, and we will not be able to solve this. And in order to illustrate this, let's say, for example, well, let's increase the maximum average fluid temperature to, let's say, 25 degrees. So this you can, for example, do if you're not that interested in the maximum temperature, then you just increase it. And then you will see that you found the solution, but now it's limited by the minimum average fluid temperature, and you can see that the maximum temperature is 18.4. So it's indeed above the threshold. So this is one solution. Just say, well, we increase the threshold for injection temperature during our cooling period. But of course, then you're not taking into account the summer comfort of your building, because you're saying, well, we do not care actually what the maximum temperature is. So that's one solution. And the other solution is just, instead of having 4 boreholes in this case, increase it to 5, and we again will find a solution there. So I hope you found this video interesting. You learned something about this error which will occur rather often, and how you can cope with it, where it comes from. If you think this is interesting, please share it with your colleagues. And I hope you subscribe, and we see each other in the next video. Take care. Bye.